Hey everybody, and welcome to another Jamovi tutorial. In this one, we are going to go through the PAMLJ power analysis module. So earlier, you saw a power analysis overview for PAMLJ, just sort of going over what to expect if you were to use this module package in Jamovi for your power analysis needs. And so in these videos, as I mentioned in that previous overview video, is I'm going to just focus on a single statistical analysis. Before we jump into that tutorial of that analysis, just want to let you know that in the past couple of months, you might have seen a video outlining that Jamovi is now in version 2.7, and I am using 2.75 for this string of videos, unless something changes. But I don't think so. We're going to be using 2.7.5, some bug fixes from 2.7, but we're going to be using that. Now, you're going to see here in these videos, I haven't updated all of my packages for the new 2.75. The only one that I did update is the power module here. Now, the power module on this top row is going to feature not only PAMLJ, but other Jamovi power packages. So how to get the power package, and when I click on it, what you can see is all of the PAMLJ ones that you're going to see a video for. So we're, except for structural equation models, we're going to do all of the rest. However, we're going to start in today's video with correlations. But before I change the windows that I'm looking at, we go into modules and we go into Jamovi library. And as you can see here, if I scroll down to all my packages, they all need to be updated to work with 2.7, version 2.7 of Jamovi. So I haven't done that yet. The only one that I did do is PAMLJ. So I went through this one. Marcello Gallucci is the one who developed this. It is in version 0.6.3, and we're going to go through all of the GLM power analysis in separate videos. I go over this particular description in the overview video, as you may have seen. So I have videos on my channel to do power analyses, and there was a previous module in Jamovi a few years ago that added, for t-tests and I think maybe correlations, but they weren't very robust. In PAMLJ, we have an extremely robust system of information, and in the power analysis that we need, right? That we can use to go up against the powerhouse in power analysis, pun intended, G-Power, right? G-Power 3.1 is the current version, and it's a little module that has a buttload of tests, and it's developed by a group in Germany. There are a lot of interesting words that are used, probably through translation processes, but just in statistical theory and teaching and learning, terms are going to vary from country to country. And so one of the biggest issues with G-Power that I find on my G-Power series on YouTube, on those videos, is that people are asking questions about which tests to use, which what information do I need to put in? And a lot of it does, I think, stem from the vocabulary used within that program. When I came across PAMLJ earlier this summer, I noticed that there was, one, a great pains to have the language from each analysis, so statistical analysis, correlation, and the power analysis be the same, right? It is uniform in the parameters, doing the sensitivity analysis, and making the plot, which is to say that the language used in here is going to be the language that is used by the English developers like Jonathan Love in Australia, which has a lot of English comparisons to the words used in American English. And I think it's really that's really important to get people where they're at, as opposed to the G-Power of this highly technical language. Of course, G-Power is used by so many people across so many different fields that use statistics. So I'm not saying that those terms are wrong or incorrect. Perhaps for me as a teacher of statistics, statistics are a language that needs to be understood at the most basic level. So that's what we're going to do in this video. Apologies for the little mini rant at the start. Let's talk about correlation, power analysis for correlation. So a power analysis for correlation is going to depend upon the effect size. Well, the effect size in correlations is the exact same thing as rho or R. And so what we can see by looking at the default, when I go to power and I hit on correlation, this shows up. This shows up, and it is all I need. You don't need a data set open at all. You can do this just as a task done by Jamovi. It's great. It's all contained within here. And so we are looking to calculate our sample size a priori before we get started. And so what we're going to do is we're going to open up the correlation power analysis, and here's where we are. Before I talk about anything else, let's look at the information that is available to us when we first open it. So by default, we are calculating n, which is our sample size. So the general reason for using a power analysis, doing an a priori power analysis. I require all of my statistics and methods students to do an a priori power analysis for their research projects. We're going to go into more details about the parameters, but these parameters will either be grayed out or be black for you to input. And of course, the grayed out ones will have an input box that is inaccessible. We also can do a sensitivity analysis, and it will create a power contour plot. And we can explore that once we're finished. And then we can do a power parameters plot, which is going to show us density curves, and we can mess around with that. The parameters are given default values to show in the results area. And so we have two tables all ready to go. We have the a priori power analysis, which is what we're going to get with the information that we input here on the parameters. Okay. And so this is the money right here of the table. What's our N? Well, under these default parameters, we need 37 people. That's what the default parameter reflects here, right? And we'll go through more when we start changing some things. The other table is the power by effect size. And this is your type 1, type 2 error chart, essentially. And it gives you a breakdown of what you would expect for the power needed to detect an effect, right? So if we had a power of less than 50%, this is going to be a likely miss. We're going to miss the true effect. What that might look like is a row between 0 and 0.32, or in this case, an R, right? Because that would be our observed statistical estimate. And then 50 to 80 would be another interval, right? 0.32 to 0.44. 80 to 95 would be in this range here. And then almost surely detect would be a 0.95% power value. And that would be a correlation greater than 0.54, right? So that's all of the information that we will get by default. So let's take some time to explore the parameters here. So by default, they're saying the effect size that they want to calculate is a row of 0.5 or achieve an R estimate, a Pearson's R estimate of 0.5, okay? And the minimum desired power is 0.9. That's put in by default. So the interesting thing here is that G-Power puts in 0.95 as default. You don't actually have to. And then sample size, since that's the one we're looking for, we are not going to gray out. This 20 is not included in any of these calculations, so don't worry about that. And then type 1 error rate is our alpha level, right? This is our criterion. We're going to leave that at always as default of 0.05. That's convention these days, and it's been convention since I did my undergraduate statistics 20 years ago, as of this recording, right? So and then by default, two-tail is the test, the correlation test that we're going to do. We could do one-tailed if we wanted to. We have the option to do one or the other. We're going to leave it on default of two-tailed. Now, only change that if you are making a one-tailed hypothesis. If you are not making a one-tailed hypothesis or a directional hypothesis, leave it as two-tailed. It is a more conservative sample size estimate, right? Because it'll be harder to detect the effects in either side of your data distribution. So leave it as two-tailed if you do not have a directional hypothesis. We'll go through the sensitivity analysis and the power parameters plot here in just a moment. The last thing before we start futzing around with the numbers here at the top, right, the effect size and the desired power is Marcelo put in these info modules so you can understand what you're reading in these. And sort of a human factors model design, he did not make it always opened when you do the power analysis processing. So that's great. You click on this and you get a little bit more power, right? And it tells you what you want to do with this calculate drop-down menu right here. So calculate N computes the required sample size for the target effect and minimum desired power. Okay, so I missed the D there. So it's all right, just a typo. You would want to calculate power by putting in it minimizes it every time. Calculate power if you are doing post hoc power. You've already collected your data and you want to, and you know your effect size because you've already done those calculations, and you want to see how much power you are able to achieve. I'm going to actually integrate this into my classes this semester because we're going to be using this PAMLJ module this coming year, which is going to be great. So we're going to do the calculate N and we're going to use the calculate power, and they're going to tell me what power they achieved in their results section. So I think it's a good teaching effort. And then you can also do this as an effect size calculator if you really wanted to, because effect size, sample size, and power, along with alpha, are the four pieces to the power analysis puzzle. They're all correlated with each other, okay? And in all cases, you can set your type 1 error rate or your significance cutoff. And one thing that I will show you really briefly here, I did show this, but I'm going to show it in every video, I suppose. You can click on the that link there in the info, and it will bring up a text-based with images, screenshots, way to interpret all of this stuff, including the sensitivity analysis and the power plots, the power parameters plot, I should say. So, and this would just be for correlation. And so if you were to open up the other ones, it would be the manual for that effect. So I'm gonna minimize this because we don't need it anymore, right? I talked about it in the overview. So let's change some information, shall we? Let's go back up to N because we want to calculate our sample size. Now, as you can see, an effect size of 0.5, an effect size of 0.5. Now, there's no tooltip here, like there is in G-Power. Marcelo, if you're watching, that would be great. For the conventions of a correlation in behavioral statistics, as offered by Cohen in like 1967, I think, somewhere around there, we have a 0.1, 0.3, 0.5 for small, medium, or large, or weak, moderate, and strong. Those are our conventions, right? So right now, this default of 0.5 effect size that we are anticipating is a large effect size in behavioral science. So just putting that out there, that by default, this is quite a large effect, but we are still looking for quite a bit of power, 90% power. That's a lot, right? So let's go ahead and change some things and pay attention to what happens to the sample size of 37. I'm going to change this to a 0.1 sample size, or excuse me, I'm going to change this to a 0.1 effect size, right? So a small or weak correlation between two variables, okay? And look at what happens. For 90% power, we went from a large effect of 0.5, an R of 0.5, to an R of 0.1. We went from 37 to 1,046. Isn't that wild? That's so huge, right? That's how many more people we would need to detect a really small effect. Now, maybe I don't need 0.9 or 90% power. Maybe we'll go to the convention, which is a little bit lower. Now, there are some debates about putting this number in, but an 80% power, that is, or 20% making a type 2 error. Let's go ahead and put in 0.8, which is the value that I teach my students. And we end up with, okay, so we're expecting less power, okay? So if we go ahead and follow this, right, of what we expect to detect here, right, 0.8 to 80% to 95%, we need a value in between row of 0.1 and 0.3, I'm rounding. We'll probably detect that effect, okay? So how many people would we need to get into that range? We would need 782 people. And this is a value that I come across quite a bit because this is the value that I tell my students to work with. If they're not sure from previous literature and they're doing a correlation, how many people do they need? Well, I tell them, go do an effect size of 0.1 and a power of 0.8, and you'll end up with 782 or thereabout. 700, around 780, I think, is where it ends. Okay. So that's how you would do a correlation power analysis a priori, right? Calculating sample size. And we can change this up to, we can do 0.3 medium effect, right? And then we can change this to 0.5 power, which is not a good idea, but you can see that 0.3 effect size and 0.5 power is an N of 42, a lot smaller, right? So let's take a look at what a correlation sensitivity analysis would look like. Let's change this to 0.1 again, okay? And change this to 0.8, which is my normal. And let's drop in a sensitivity analysis. Let's take a look at the power contour, okay? So the color gradient here is from purple, which is the coldest, to power being the highest, right? So 0 is purple and power of 100% is yellow, right? And that's why this whole section here is yellow, because this is my sample size down here and my hypothetical effect size here, which is rho, right? And so you can see here as we contour, the reason why this number was settled upon was because that is where we hit our power, which is 0.8 right there. There's our power curve, 0.8, okay? And we can come down here, right? That's our curve. And so where does that curve hit 0.1? Well, we go across and then boom, and then we go down. Look at that. And so this is why if we go up to 0.3 and we hit the curve, you go down here. That's why it was like, 70 something or whatever it was, okay? Well, I actually did 0.5, so that curve was somewhere over here. Now, the power contour plot is only going to plot the information that you have here. So if I change these numbers back to 0.3 and 0.5, it's going to put the contour curve on 0.5, right? That's the color of 0.5 is like this teal, right? That's where it is. And here's the contour. 0.8 was over here somewhere, right? And you can see that if we put 0.3 up here and goes down, there's our value of 42. You can see that all that power goes up to a hypothetical effect of 0.9. Okay. If the numbers are big, we'll have log scale when needed. It doesn't need to do log scale right now, but that's what happens. You can do a power curve by effect size. And so it takes this curve and cubes it, right? So it becomes a cubic function here, right? And so we do have effect size down at the bottom and power along the side. And it tells us where on this curve, what our sample size needs to be, right? And you can do power curve by n as well, which is, I think, a log function. Maybe they're both log functions. I'm forgetting my algebraic functions these days, but yeah, you can see that sample size and power is what it looks like here, and that's the color that we're looking at for 0.5. And there it is. So those are the sensitivity analysis curves that you can get, but you can also plot different things if you want. You can plot n by effect size, and there it is, okay? N by effect size, and you can show values. I don't know why you'd want to. 61, it only looks like it only shows some. Those are values of n, by the way, right? And then you can also separate it by, please set a value for values for each curve, 0.05. Let's do that. Yeah, buddy. Oh, values for each number of curves, 2. Please set a value for each curve. Okay, so if I did 0.1, what would happen? So that would change based on that. And they're sort of overlapping, but you have 61 versus 43 for an effect size curve, okay? And then 5 and 7 are overlapping. So that's the difference between an alpha of 0.05 and an alpha of 0.1, but we can add a third curve in, okay? And then we can do 0.01 to get a little bit more conservative, and you could see how that power would change. And so 0.01 now adopts the blue. 0.05 is now the gray, and 0.1 is the orange as it was on the last curve. And you can see that we now, for an alpha of 0.01, we need more people because we have a more conservative effect. 104 is needed. And over here, overlapping, it looks like that is 10, 7, and 5, something like that, for an effect size of 0.75. So yeah, power parameters, really cool plot, really cool plot. You can do that. You can also show it in table form, which would be all of those values and which ones are being plotted along the lines here. I don't think you really need that to make a case for power analysis. And that's how you do a correlation power analysis in PAMLJ, this module that you can, this package that you can add to your Jamovi to make it a little bit more robust. If you have any comments, questions, suggestions, or other feedback, please leave those down in the comment section below. I'll see you in the next video. Thanks for watching. Bye.